All right, let's just dive right in. We all think we know the number one rule about black holes. Nothing escapes. But what does Einstein's math actually say is going on in there? Turns out, the predictions are way, way stranger than any science fiction you've ever seen. We're talking tunnels to other universes, and maybe even the end of time itself. So, let's get right to the heart of the mystery. Imagine we launch your arch nemesis on a one-way trip straight towards a black hole. What would we actually see, watching from a nice safe distance? Well, the answer is one of the biggest, most mind-bending paradoxes in all of physics. Now, as your nemesis gets closer and closer, you'd think they'd speed up, right? I mean, gravity is getting stronger, but that is not what you see. Nope. Instead, from your point of view, their rocket looks like it's slowing down, almost like it's grinding to a halt against some kind of invisible wall. And then it gets even weirder. The light coming from their spaceship starts to stretch out, getting redder and dimmer. This effect is called gravitational redshift. Eventually, that light gets so stretched out that it just completely fades away. So here's the crazy part. From where you're standing, your nemesis never ever actually crosses the event horizon. They just seem to stop, frozen in time, right at the edge, forever. Now, this seems to suggest that nothing can ever truly fall into a black hole. But is that really what's happening? So this whole puzzle, we're going to call it the frozen voyage. It's a conclusion that comes directly from our best theory of gravity, but it just feels wrong, doesn't it? To solve it, we're going to have to completely rethink what gravity even is. You know, for centuries, we had Isaac Newton's idea of gravity, some kind of mysterious force pulling things together across empty space. But then Einstein came along and just flipped the whole script. He said, look, gravity isn't a force at all. It's the actual fabric of reality, of space-time, being bent and curved by anything with mass. And that is the absolute heart of general relativity. It's this beautiful two-way street. Matter tells space-time how to curve, and then that curved space-time tells matter how to move. It's the official rulebook for the entire cosmos, and, well, it's the reason we have this frozen voyage paradox in the first place. Okay, so to really get what's happening at the edge of a black hole, we have to learn how to navigate Einstein's warped reality. And that means we need to take a closer look at the tools we're using to see it. And here's the big twist. That frozen view isn't what's really happening, it's a distortion. See, the math we use to describe space-time is kind of like a map. And just like any map of the Earth you've ever seen, it's not perfect. In fact, all maps have flaws. Just think about the good old Mercator map we all saw in school. Super useful for sailing, right? But it massively distorts size. On that map, Greenland looks just as big as Africa. But in the real world, Africa is 14 times larger. The map is useful, sure, but it's lying to you. Our first look at the black hole, it's the same kind of lie. And this is the key, the absolute breakthrough pointed out by none other than J. Robert Oppenheimer. The frozen voyage is only what someone watching from far away sees. If you were the one actually falling in, you'd sail right across that event horizon and you wouldn't feel a thing. You'd have no idea you just passed the point of no return. Two completely different experiences of the exact same event. So how on earth can both of those things be true? Well, physicists figured out that if you just choose a different mathematical map, a different set of coordinates, the whole problem at the event horizon just goes away. It was never a real physical barrier. It was just a glitch, a distortion, created by using the wrong map. Things can and absolutely do fall in. All right, now that we've actually crossed the event horizon, let's see where our new, better map takes us. We are officially inside the abyss. So once you're past that point of no return, the rules of the game change, big time. Inside a black hole, space itself is flowing inward, faster than the speed of light, and it's dragging everything with it. It doesn't matter which way you fire your rockets, all possible paths, every single one of your possible futures now points to one single, inevitable destination. And here is maybe the wildest part of all. That singularity at the center, it's not a place in space you can try to steer away from. It's a moment in your future. It's an event. Just like you can't avoid next Tuesday, once you're inside a black hole, you cannot avoid the singularity. For you, it is the end of time itself. But wait, it gets crazier. When physicists pushed the math of a black hole as far as it could go, they found more than just a singularity. They found its perfect opposite,
A white hole. You can think of it like a cosmic fountain, a spot in spacetime that you can never enter from the outside, and where anything that happens to be inside is violently and unstoppably shot out.
And the math didn't stop there. It also predicted this incredible connection between the black hole and the white hole, a tunnel through the very fabric of space-time. This, my friends, is the famous Einstein-Rosen bridge, or as we call it, a wormhole, a literal shortcut, maybe connecting two distant places in our own universe, or maybe, just maybe, connecting our reality to a parallel universe. So yeah, this is where things go completely off the rails into science fiction territory. The very same math that correctly describes black holes also seems to be describing tunnels to other worlds. But does that mean they're actually out there?
I mean, that is the billion-dollar question, isn't it? It's one thing for these ideas to look good in equations on a chalkboard, but could you actually go out and find one in the cosmos? Is our universe really riddled with these bizarre gateways to who knows where?
Well, probably not. And there are some really big catches. First, the math that predicts them describes these eternal black holes that have existed forever, which is totally different from the ones we see that form from collapsing stars. Second, that wormhole bridge, it's ridiculously unstable. It would pinch itself shut faster than even a beam of light could make it through. And finally, to prop one open, you'd need something called exotic matter with negative energy, which, as far as we know, is physically impossible. Yeah, as one expert puts it, while it might be possible in a purely geometric sense, the second you start applying the actual laws of physics about how matter behaves, the whole idea just kind of falls apart. The reasons they're not possible are, in his own words, very strong. So it really seems like these incredible predictions, these white holes, traversable wormholes, these bridges to parallel universes, they're likely just a cosmic mirage, a beautiful, fascinating ghost that lives only inside the mathematics. But does that make it all pointless? I mean, if these tunnels to other worlds aren't real, what have we actually learned from all this? What's the point of studying a map to a place that doesn't even exist? Well, the takeaway is that this is how science works. It's a journey, an exploration. You have to remember, the smartest physicist on the planet, including Einstein himself, once thought that black holes were just a mathematical quirk, an absurdity that could never actually exist in the real world. And they were completely wrong. So it really makes you wonder, if our maps of reality have already led us to something as bizarre and impossible as a black hole, what other destinations are out there, waiting on parts of the map that just haven't been written yet?